Hello guys, welcome back to the fourth part of chapter 12, and in this video we're going to be doing just about the Heisenberg uncertainty principle. And this video is going to be a quick summary, just straight to the point with an example problem. So in this class, or in chemistry in general, we never know where the electron is particularly, so all the models that describe where the electron is, I think one of them, the Bohr model, is just wrong. So electrons, you can only calculate the probability of an electron being in a certain place. Like, you can't tell exactly where the electron is, you can just tell that there's a high probability it will be in this orb, this sphere type place. And that's what we call the delta X, the probability of the electron being here. And in classical physics, they were usually able to predict things like problems in classical physics could be predicted or solved to the point, but they figured out back then that you can't exactly find where the electron is exactly, but you can calculate where it is. And then this guy, who the principle was named after, Werner Heisenberg, determined that it's impossible to know both the position and the momentum of an electron at some point. So instead, we describe a probability of where the electron will be. So the equation is the delta X times the delta P, which is the probability is greater than or equal to H, which, like we used before, is still Planck's constant, over 4 pi. And since the exact path of an electron is unknown, this delta X is the uncertainty in position, while the delta P is the uncertainty in the momentum. Now I'm going to show a practice problem to further demonstrate this concept. As you can see right here, this is still the same formula where the delta P is the uncertainty in momentum and the delta X is the uncertainty in position. It says it here too, gives the H, Planck's constant. And also, another thing that you probably have to do with this equation that is not mentioned here is to find the delta P, which is the uncertainty momentum. Remember that momentum itself is equal to the mass times the velocity. So that means the uncertainty in the momentum is going to be equal to the mass times the uncertainty in velocity, which you get here. And then to find, let's say you're looking for the momentum, you tweak this equation, it becomes delta P is greater than or equal to, you divide this to get rid of it from this side, you divide the delta X and put it on here, become H times 4 pi times delta X. And if you're looking for delta X, you do the same thing where you move P to the other side by dividing it, and it'll also be H over 4 pi, but this time times delta P. So now let's do this problem where it asks to calculate the uncertainty in position. And if you remember here, like we did, to calculate the uncertainty in position, we use this one where it is delta X is equal to H over 4 pi times the uncertainty in momentum. And for this one, since we have both the mass of the neutron and the velocity of the neutron, like it's asking here, we can find the uncertainty for the momentum. So I'm going to do that right now. Equal to the mass times velocity, which is the mass is 1.675 times 10 to the negative 27 times the velocity, which is 0.200. Remember the units, they both end up giving, you have to multiply this by that. You have to multiply kilograms by meters per second. And here the answer will be given in kilograms times meters per second. But for this equation particularly, the units don't really matter. But I'm just mentioning it for further topics or further questions in the class where the units do matter. You have to always keep the units in the back of your head. And when you put this into the calculator, you get 3.35 times 10 to the negative 28. And right here, we go back to this equation where it's delta x is equal to h, which is, like we know, 6.626 times 10 to the negative 34 over 4 pi times this 3.35 times 10 to the negative 28. And we just plug this into the calculator and we get the answer for the delta x. After we plug it in, we get 1.57 times 10 to the negative 7. And now we keep that in mind and we move on to the next problem. And we do the same thing since we're both given the same thing. We're given the mass and the delta V. And keep in mind, by the way, the mass for these has to be given in kilograms. So if they're given in grams, we have to convert it to kilograms to use meters per second, because remember the units have to be kilograms times meters per second. So if it's not in kilograms, you have to convert it to kilograms. But luckily we're both given it in kilograms. So we just do the same thing where we find the delta, P, which is the momentum, which is the mass times the uncertainty and velocity. So the mass here is given at 0.43 times the velocity 0.2, which gives us for the uncertainty momentum 0.086. And now we put this into this equation, which is 6.626 times 10 to the negative 34. The delta H, if you remember, divided by 4 pi times this 0.086. And after we plug that in, we get 6.13 times 10 to the negative 34 meters at the end for both of them. Actually, the units, after they all cancel out, the uncertainty position gives the meters. And now when we compare these two values after getting them at the end, we can see that 10 to the negative 34 is a lot smaller than this, which means this uncertainty is a lot smaller than that. And that makes sense because the soccer ball is bigger, and usually we know where a soccer ball is going to be compared to the mass. But for the electron right here, the neutron, it's a lot harder to know where the neutron is, which is why the uncertainty is much greater than that. And that's what C is asking about. So if you can see and understand what this means it's more uncertain to know where the position of a neutron is than a soccer ball. And if you get a question like this on the test, you should be able to kind of half confirm your answers by making sure that for things that you kind of be sure with where they would be, you should get a lot smaller uncertainty than things that you're not sure where they'll be, which are like things like electrons and neutrons.